welcome to the group exhibit Hydrogen Fuel Cells and Batteries 2017 at the Hanover Fair. My name is Muriel Burkas, and I'm looking forward to our second presentation of this day with Anthony Anderson. He's Director of Marketing and Business Development at Precision Combustion, and he will talk today about compact diesel jet fuel processing systems and SOFC generators. So I'm very much looking forward to your presentation and hand over to you.
Great. Thank you, appreciate it. Thank you, Muriel. My name is Tony Anderson. I'm here at the fair with my colleague Shabira Chowdhury in their booth D33. We'll be talking about compact diesel and jet fuel processing systems and also about some SOFC generator work. A little bit about Precision Combustion. We're a small business, privately owned, around 40 employees in North Haven, Connecticut, USA. Some of the areas that we're working on. Many customers, primarily U.S. government, but also large and small companies as well, and universities. Kind of a matrix that you can divide up in a lot of different ways of the areas we're working on. In the power area, which is of interest here, obviously with hydrogen and fuel cells, working on fuel reforming and fuel processing and fuel cell systems for APUs, gensets, vehicles as well, soldier portable things. Also, UXV is what I'll call it, unmanned anything. So you can take this and use this in unmanned systems as well. Reformers for industrial systems. Also for hydrogen generation, still gas processing for fuel refineries. Chemical manufacturing, Sabatier methanation for power to gas. We're also working on that, primarily funded by NASA. And also gas to chemicals and CO2 to fuels. And all the others that you see. Also a desulfurization for fuel cell systems as well. Give you an idea about the areas in the fuel generators. We have the fuel cells from small ones, 20 to 50 kilowatt, 1 to 2 kilowatt, and 10 kilowatt size systems. Engine generators also, and then we make burners for Stirling engine systems. So we may compete against each other in some ways, but a lot of good efforts going on here. There we go. The platform technology that we use for these catalytic reactors is what we have trademarked as microlith. It's a catalyzed mesh, which you can see on the left. If you take one of the wires and you cut through it, you'll see that the top right is the metal with an interfacial layer, and then the wash-coated catalyst layer is with that. And we make it on a roll-to-roll process to have the technology that's high quality, but also low cost. And a little close-up as to why this is the benefits and why it's better. And when you compare it to a monolith, so that would be like the monolith you see in the catalytic converter of your car, would look something on the picture on the left. And then the microlith would be on the right. And when you do CFD analysis, you see that you have boundary layers that build up with the monolith, and with microlith, you don't have any boundary layers. And so you have a high surface area per unit volume, high heat mass transfer rates. Then we have 3 different reforming technologies we're developing. The catalytic partial oxidation, which we define as fuel and air. And then catalytic autothermal reforming, fuel, air, and steam. And then steam reforming, steam and fuel, in various sizes that we've developed, and also for various applications. You can kind of see how we're scaling with the diesel and jet fuel reformer, going from 100 watts to 1 kilowatt. High sulfur 1 kilowatt, 2 and 3, 10, and even 300 kilowatts that we developed for a shipboard program. There we go. One of the technologies that we've developed is to be able to clean up the sulfur. And so having sulfur in liquid fuels, we can go all the way to 3,000 ppm sulfur in the fuel, reform it, and then remove it before you get to a fuel cell stack much below 1 ppm of sulfur. So you can see an example of one of the adsorbents that we have. And we have there we go, there's a breakthrough curve. So if you used zinc oxide on pellets, for example, you'd have a breakthrough curve that looks something like that. We're using it with our type of catalyzed bed. It's a very sharp breakthrough curve. And so you can have a very defined area and know exactly when you need to replace that cartridge. So think of it as an oil filter in your car. And you size that cartridge based on your application, how much weight you can carry, how much time you need to operate before maintenance cycles, etc. In the hydrogen purification area, we have water gas shift technologies, preferential oxidation of CO technologies as well. We've worked with membrane separation technologies, PSA, so we have experience with that in making higher hydrogen, PEM type quality reformate applications. So some of the commercial applications that we're looking at and developing toward aircraft APUs, truck APU is kind of hard, but we're working on it, and mainly coming out of the military because they have analogs to all of these, and so we're developing under a lot of military applications, but then fortunately have commercial applications as well. In the marine area, fuel cell range extenders, recreational vehicle or caravan APUs, and also industrial syngas generation as well, or HYCO. So our reformer benefits, so typically we bring the most benefit in areas of where you need something to be compact and lightweight, so essentially mobile applications or personal applications. Readily integrated with fuel cells, it's modular, so it's serviceable. So if you need to replace a reforming cartridge, you can do that. If you need to replace a sulfur removal cartridge, you can do that. The stack quality reformate, we use commercial off-the-shelf balance of plant controls. That's very important if you're going to have a cost-effective solution. You can't have special devices like that. And then also technology readiness level, it's anywhere from 4 to 8 depending upon where we are. So we have essentially fielded systems that are now under qualification, so that's why I call it a TRL-8 rather than a fully commercial product. There's an example of a fuel reformer and a fuel processor cart. So we actually take the reformer and use a laptop PC control, mass flow controllers, and it's a way for customers to become comfortable with our technology as to how it works, how it operates. They can validate our claims as far as what the reformate compositions are. They can also, if they're testing a downstream technology like a membrane separator or fuel cell stack, they can obtain one of these from us and actually test their technology using real reformate rather than simulating it by mixing a bunch of bottled gases together. An example of a couple more turnkey skids we've done. These were 2 oxygen blown natural gas syngas generators delivered to an industrial company. And they were doing some development of another technology downstream that needed a particular hydrogen to carbon monoxide ratio. And so these 2 units have operated over 5,000 combined hours, 60,000 cubic meters of syngas for their particular development process in intermittent operation. We've also done other scale-ups. So this is a megawatt thermal VOC reformer. This is for an automotive company. They had solvents and liquid solvents they wanted to do something with. They were paying to have people burn it as hazardous waste or regulated waste. So we have a reformer we developed for them as part of an industrial equipment package to reform the solvents that they captured, and then it could be put through a molten carbonate stack to generate electricity from. So it's kind of a triple benefit of saving money, of having to pay somebody to take it away. Also, you make a little bit of electricity for that particular factory, and then you have a nice green marketing story as well. Another scale up, this is a 5 megawatt thermal reformer. So this is a natural gas, partial oxidation, so no water. And so that had 1,000 hours of testing completed as well for that particular operation and that particular customer. So in our steam reforming area, just to give you an idea of what we're doing, is we're taking the microlith mesh and both using it as a reforming catalyst, and then in an oxidation catalyst mode, so in a tube within a tube type of an embodiment. So you can see the benefits of doing that between having a wire mesh pack channel and having an empty channel, having increased heat flux through that. And so it's a way of having a catalytic burner rather than a flame burner, avoiding flame impingement and some of those issues, and also having a smooth heat transfer. So a simple hydrogen generation system, P&ID, to show you that using the heat and the steam reforming, we can use water gas shift and actually make more pure hydrogen. A couple different size reformers we made, one for power generation, one for more hydrogen generation, higher. You can see it's higher pressure with thicker flanges. So this was actually for desulfurized diesel or distillate type fuels. And so we actually have some real data here and show you can see the reformate compositions. Running it through a membrane separator was not our technology, it was a partner's technology, but you can see that nearly 80% separation efficiency integrating it with our technology. It made about 17 standard liters per minute of hydrogen. So there's a picture of the setup with the steam reformer and then our partner's hydrogen separation technology. Another effort that we're working on is packaging the 1 kilowatt diesel and jet fuel reformer with the desulfurizer. You can see a couple pictures of it. There's an exploded view of a real version. You'll see a mock-up in our booth in D33, which is a nice little orange box at the bottom. So this is the reformer itself. It does not have a solid oxide fuel cell stack in it. see where this goes here. There we go. So the maturation time frame, this is a multi-year development effort that we've been going from on the far left, you'll see using facility-supported reformers and mass flow controllers, doing more lab-based controls in a standalone basis, then repackaging it in 2015 with a balance plant and single control board. And then by 2019, in a current project that we have, to have an integrated package with our reformer and with a solid oxide fuel cell system, to have an integrated fuel reformer and fuel cell system 2 years from now, ready for field test. Sorry about that. So again, showing you the integration of the reformer with the solid oxide stack, 1 kilowatt operating at about actually 995 watts, fuel utilization 72%. And then also we operating on 400 ppm, so what we'll call low sulfur jet fuels that both just showed essentially the compositions are very similar, whether operating at full load, so 3 kilowatt thermal would be for a 1 kilowatt electrical stack, or 1.5 kilowatts thermal, you're operating at half load essentially. There we go. And so then some of the reformer specifications, it's an autothermal reformer, so it has the fuel injector, steam generator, heat exchanger, desulfurizer, the sensors, controls, the pumps and blowers, again, the commercial off-the-shelf pumps and blowers. In a compact package under 10 kilograms, we can utilize up to 3,000 ppm jet fuel, which is some of the military fuels are that high specification. There might be some commercial ones out there as well. Sulfur cleanup, we get much less than a half a ppm sulfur in the reformate. So it'll be long-term use. We've operated 1,500 hours without failure using those 3,000 ppm fuels. And you can see it also the mock-up in booth 33, D33. We're also scaling up, doing a 2 kilowatt system, so you can see the reformer and desulfurizer in the far left. In the center is our test rig, so it's a solid oxide fuel cell in our hot box. And we also developed a dual fuel burner to be able to take either the liquid jet fuel or anode gas as appropriate. So we've operated that for 270 hours. There we go. And you can see very stable performance with Tier 2 diesel, operated in a 125-hour test. And then switching over to a higher 400 ppm or 100 to 400 ppm sulfur jet fuel. You can see very stable operation. We had a malfunction because it was tied into facilities power. So we had a shutdown. Immediately we fixed what was wrong, started back up again, and came back to, again, having stable performance. So we did a stable performance there, I guess, 50 hours after that. And again, stack voltage was stable at 60 volts, 25 amps. No observable degradation. Again, we not only doing system integration, but we can provide burners on a select basis. Essentially dual fuel start burners, anode gas oxidizers. So we provide prototypes to various fuel cell system companies that are interested in that technology. There we go. Well, also, as I mentioned, we're developing Sabatier methanation. So that was an example of a tabletop version that we developed and supplied for a customer for evaluation of our technology. So essentially, Sabatier reactions take in carbon dioxide and hydrogen, and you catalytically react it to make synthetic natural gas. So this is one method of doing power to gas or energy storage is synthetic natural gas. It's demonstrated at the laboratory scale, so full scale to someone like NASA would be what carbon dioxide that 4 people would put out in a cabin. And of course, that would be laboratory scale for an industrial application. And so summarizing, you can read the summary slide, but we have been successful with developing and integrating these jet fuel systems with the reformers, and now integrating the stacks with our partners and our customers. And so there was the information slide. Please come by booth D33. My colleague Samir Chowdhury, Vice President, Research and Engineering, is joining me there if you want to do a deep dive into anything technical.
Thank you very much.
Thank you, appreciate it.
Tony Anderson. As he already announced, yes.
Thank you.
He will be available at booth D33. Are there any questions right now you want to ask?
I don't know how we're doing on time, but here we go.
What about the startup time of your diesel fuel reformer? How long does it take to start up from cold start?
From a cold start, it's usually within 1 or 2 minutes. It has stable operation to make reformate for a fuel cell, so the transients are far faster than a typical stack would have, especially a solid oxide stack, which is what we use mainly for these liquid fuels. Again, you can make it operate on PEM stacks, operate on reformed fuels. I found that most people are more successful with just using plain hydrogen to make PEMs operate as opposed to reforming a fuel for hydrogen. Yeah.
Any further questions? Otherwise, I would thank you one more time for your presentation and just announce the next presentation. It will be about the blue move for a green economy, and we start in about 5 minutes. Thank you very much.
Thank you for your time and attention. Appreciate it.